Hey guys, how's it going? So, our next topic for this course will be discussing energy, and in particular how we can use this concept of energy and this idea of conservation of energy in order to solve these physics problems we've been seeing or to analyze physical systems in a fancy way. So, I guess to start off, as we saw in the last chapter, there's this thing called kinetic energy that we can calculate by saying that the kinetic energy of an object is equal to 1/2 the object's mass times its velocity squared. Now, what that means is that in order for an object to have kinetic energy, it must be moving, which I guess is, pretty easy to remember. So if an object isn't moving, then it doesn't have any kinetic energy. It's very simple, okay? But energy comes in many, many, many forms, okay? And most of these other forms are in the form of potential energy. So when we think about potential energy, there's so many different types. We can have a ball sitting on top of a table that falls down, and we would say that at the top of the table it has gravitational potential energy. Okay. There's also the energy, in chemical bonds that you guys learned about in chemistry, and so there's chemical potential energy as well. We can think of a little nuclear reactor plant. Okay, you got smoke coming out of it in a building here, and there's nuclear potential energy. There's, you can imagine two balls attached to a spring, maybe, and this would be elastic potential energy, and there's other types as well, okay? But the idea is that there's many different types of energy, and the cool thing is that these different types of energy can be converted into one another. In fact, that conversion of one type of energy into another is the basis of life on Earth. It's the basis of modern society. It comes through in a lot of ways. So I really like this chapter or this unit. I hope you guys do as well. And as you'll soon see, using this idea of energy and conservation of energy really does make your life simpler. So let's go on to the next slide here. Okay, so kinetic energy you guys are familiar with already. Of those potential energies that I showed you, the one that we're going to focus on first is gravitational potential energy. So I will usually abbreviate this like that as PE gravity. Okay, we will have to specify what type of energy we're talking about here. And gravitational potential energy is given by a very simple equation, mgh, where m is the mass of the object, h is the height above the reference point, and I'll get to that in just a second, what this reference point is. So height above reference point, and g is our acceleration due to gravity. Acceleration due to gravity. Okay. Now here's a critical thing here, and it has to do with this reference point. Potential energy, where potential energy is zero, and this applies to any potential energy that you can think of, really depends on us. We choose where that point of zero potential energy is. So if I have a ball, okay, kind of hanging up in the air, and I want to calculate its potential energy, I could choose to have that reference point be right there. I could choose to have it be right here. I could choose to have it, maybe there's a little hole in the ground, I could have it be down here. We will choose that 0 point, that zero reference point, based on what's most convenient for us. What part of the problem or what will work best for us in this problem. Okay. So we could say that maybe it's going to hit the ground, like in our next problem, and we'll say that that's 0 joules. Just to kind of remind you guys that joules is the unit of energy. Okay, it's going to be equal to a Newton meter, so another fun fact. Okay. But I could choose any one of these points to be 0 depending on what is most convenient for us. This is the ball. I don't want you to confuse that with the 0. Okay. So that's the big thing to remember with gravitational potential energy is where, you always have to note where you set your reference point at. And then this simple equation is how we're going to calculate it. Okay, so let's see how this is all going to work. Now, one of the first problems that we came across in this course is, kind of dropping a ball or dropping some object from some height above the ground. Now, the first time we did this, we used kinetic equations. Now we're going to look at it in a different way. We're going to look at it through this lens of conservation of energy. And so once again, we'll draw, a nice little diagram here. So we'll have a ball, we'll have the ground, and I'm going to say that this ground is where my gravitational potential energy is going to be equal to 0 joules. Okay, so I've set my reference point to be the ground, and that means that this ball is starting at a height of 5 meters above the ground. Our acceleration of gravity is 9.8 meters per second squared. Okay. And I think that's the cool stuff. All right. Now, when we covered momentum and we did the conservation of momentum, we had this before-after idea. Now we're going to do the same thing here. And what I do, because I tend to become a visual person, and I know some of you guys are as well, is I make a little bar diagram. And so what I'll do is I'll think of what types of energy could exist. And right now we only have these two, kinetic energy and gravitational potential energy. Now my kinetic energy initially is 0, so I'll just put 0 joules right here. My gravitational potential energy, I have some. It doesn't matter, you have to be exact, but just kind of a little bar to note that, oh, I have some gravitational potential energy there. And now for my after. Extend this out a little bit. Kind of make a little table here. So my after, I make this bar chart, this kinetic energy, and then I'm going to have gravitational potential energy again. Now this is going to be 0 joules, okay, because right before it hits the ground, it's going to be at my reference point. And that means that all of this gravitational potential energy had to turn into kinetic energy, because what the law of conservation of energy says is that if you don't have any external forces acting on your system, and our system right here is the ball, and the Earth creating the gravitational field. If there's no external forces, then the total energy of the system has to be the same. So and this is a rather simplistic example, but here's the cool thing that you can do, is you make this bar chart, and then you just kind of translate these quantities into the equations. So that's going to be mgh is equal to 1/2 mv squared. Now these are zeros, so I'm not going to put them in. And now we have the equation we have to solve. Okay, how fun is that? So this will do a little algebra here. 2 mgh is equal to mv squared. And oh look, the masses, we didn't need a mass of the ball. I bet you guys were wondering about that, weren't you? And we get v is equal to the square root of 2gh. So this will be the square root of 2 times 9.8 meters per second squared times 5 meters. Running out of room here. It's going to be equal to v, and we get that v is going to be equal to 9.9 meters per second. And look at that. No kinematic equations, nothing like that. Just two little equations we have to memorize, and just using the conservation of energy, we can solve for this problem. Okay. Another problem, and this one has to do with the vertical circle. Ooh, vertical circle, very scary. But you'll see in this problem how we can really simplify, the problem down. So let's again draw our picture. Okay. So maybe, and just pretend like this is a circle. I know it's an oval, just pretend like it's a circle. So this is V. Actually, you know what? I'm saying that it doesn't really matter what this is. It doesn't matter what, it could be a square for all this matters. And so we have, now I'm going to make my potential energy reference not at the ground, but at the bottom of this loop here. Okay. So that's going to be my 0 reference point for potential energy, because now I know that with a radius of 20 meters, that the height above will be 40 meters. Okay, so this is going to be my h. Once again, we have g is 9.8, meters per second squared. Okay. And we'll once again do our diagram. So our before and our after, line between them. So before, we have both kinetic energy, because it is moving, and we have potential energy, so gravitational potential energy. I'm not sure what the relative values are, but just the fact that it has both of them is what you have to recognize at this point. Then after, since we made our reference point, the bottom of the loop, it's not going to have any gravitational potential energy, so that's going to be 0 joules. And our kinetic energy, let's put kinetic energy final and initial to kind of separate them, will have to kind of be the combined height of both bars here. And once again, we pull all the equations down. 1/2 mv squared plus mgh is equal to 1/2 mv. I'm going to call this v final. Call that the initial. Okay. We go and plug in all our numbers. So 1/2. Oh, and once again the m's cancel out. So very cool. So 1/2 times 10 meters per second quantity squared. Don't forget the square. A lot of people do that, and I count myself in that. You got to be very careful to make sure you square these quantities, and not just the unit, the number too. This is going to be 9.8 meters per second squared times a height of 40 meters is equal to 1/2 VF squared. Okay. Solving for VF, and I trust you guys can do that, but solving for VF, you should get 29.7 meters per second. So look at this. You're solving a vertical, apparently non-circle problem, and you were able, again, with just using the simple relation, conservation of energy, and using these couple of equations. Okay. All right, so kind of to wrap up here, energy comes in many forms and is able to be transformed from one type to another. Okay. It is also a scalar quantity, so notice I didn't use any vectors there. Okay, so that's very nice. The law of conservation of energy can be used to solve problems in the absence of forces external to the system. Now, once we do have forces, which is kind of the next thing we do, we have work, and things change a little bit, but it's still not too bad. And then potential energy of all types is always measured relative to an arbitrary reference point, and we can choose that. That's up to us. And we can choose that reference point, and we choose to define it as 0, and we measure everything relative to that. So it is possible to have a negative gravitational potential energy if it ends up to be below your reference point. And if that's the way you guys want to roll, no problem. You can still do these problems. All right. So I hope that helps. I hope it was clear, and if not, feel free to ask me any questions.